we are going to learn cryptography and security in blockchain in course blockchain. In Module 3 we have these topics: 1. Cryptographic algorithms used in blockchain. 2. Digital signatures and cryptographic hash functions. 3. Security challenges and solutions in blockchain. Several cryptographic algorithms are used in blockchain technology to ensure the security and integrity of the data stored on the network. Some of the most commonly used algorithms include: 1. Hash functions. A hash function is a mathematical algorithm that converts an input of arbitrary size into a fixed size output in blockchain. Hash functions are used to create a unique digital fingerprint of each transaction and block, which is then stored on the network. 2. Public key cryptography. Public key cryptography, also known as asymmetric cryptography, uses two keys, a public key and a private key, to encrypt and decrypt data in blockchain. Public key cryptography is used to ensure the authenticity of transactions and the identity of users. 3. Digital signatures. A digital signature is a mathematical technique used to verify the authenticity of digital messages or documents in blockchain. Digital signatures are used to confirm the ownership of digital assets and to ensure that transactions are valid and have not been tampered with. 4. Merkle trees. A Merkle tree is a data structure used to efficiently verify the integrity of large amounts of data in blockchain. Merkle trees are used to store the transactions in each block and to create a digital fingerprint of the entire block. Overall, the use of cryptographic algorithms in blockchain technology is essential for ensuring the security, privacy, and integrity of the data stored on the network. Digital signatures and cryptographic hash functions are two important cryptographic techniques used in blockchain technology to ensure the integrity and authenticity of data. A cryptographic hash function is a mathematical algorithm that takes an input of arbitrary size and produces a fixed size, output, called a hash or a digest. The output is unique to the input and any change to the input will result in a different output. In blockchain, hash functions are used to create a digital fingerprint of each transaction and block. These fingerprints are stored on the network and can be used to create a digital fingerprint of each transaction and block. These fingerprints are stored on the network and can be used to verify the authenticity and integrity of the data. A digital signature, on the other hand, is a mathematical technique used to verify the authenticity of digital messages or documents. It is created by using a private key to encrypt a hash of the message or document. The resulting signature can then be verified by anyone who has access to the corresponding public key in blockchain. Digital signatures are used to confirm the ownership of digital assets and to ensure that transactions are valid and have not been tampered with. Together, digital signatures and cryptographic hash functions provide a strong level of security and integrity to the data stored on the blockchain. By using these techniques, blockchain networks can ensure that data is authentic, tamper-proof, and secure from unauthorized access. Blockchain technology offers a high level of security, but there are still some challenges and potential vulnerabilities that need to be addressed. Here are some of the key security challenges and solutions in blockchain. 1.51% attack. A 51% attack occurs when a single entity controls more than 50% of the network's computing power, allowing them to modify the blockchain and potentially reverse transactions. Solution. One solution to this problem is to use a consensus mechanism that requires more than 50% of the network's nodes to validate a transaction or block. Sybil attack. A Sybil attack occurs when an attacker creates multiple fake identities or nodes on the network, allowing them to gain control of the network. Solution. One solution to this problem is to use a proof of work or proof of stake consensus mechanism that requires nodes to prove their computing power or state in the network. 3. Smart contract vulnerabilities. Smart contracts can contain vulnerabilities or bugs that can be exploited by attackers, potentially causing significant financial losses. Solution. One solution is to perform smart contract audits and testing to identify and fix vulnerabilities before deployment. Additionally, using formal verification methods can help ensure that smart contracts are secure and function as intended. For private key security, private keys are used to sign transactions and must be kept secure to prevent unauthorized access to digital assets. Solution. One solution is to use a hardware wallet or cold storage device to store private keys offline and away from potential attackers. 5. Regulatory compliance. Blockchain-based applications may be subject to regulatory compliance requirements, such as anti-money laundering and Know Your Customer (KYC) laws. Solution. One solution is to use blockchain analytics tools to monitor transactions and identify potential violations of regulatory requirements. Overall, addressing these security challenges requires a combination of technical solutions and best practices, including robust encryption, secure key management, regular auditing and testing, and compliance with regulatory requirements. By implementing these solutions and best practices, blockchain technology can offer a high level of security and trust for a wide range of applications. Thank you for watching. You stay tuned for next part.